Look up at the night sky. What do you see? Emptiness, silence, a void between the stars. For most of human history, that's what space was. A cold, black, and essentially silent canvas. But this silence is an illusion. What if I told you that the universe is not silent at all? That it is in fact filled with a sound? Not a sound you can hear with your ears, but a whisper so faint and so ancient that it underlies everything we see. A constant low hum that has been streaming through the cosmos since the very beginning of time. This is not the story of the Big Bang itself. That first unimaginable moment of creation is lost to us, a singularity of physics that our science cannot yet pierce. This is the story of what happened next. This is the story of the very first light. Imagine trying to listen to a symphony from a mile away, but all you can hear is the final, fading note, stretched out and diluted by time and distance. Now imagine that note has been traveling for over 13 billion years. That is the nature of our quest. We are not witnessing the explosion. We are hearing its echo. This echo has a name. The cosmic microwave background radiation. It is the oldest thing we can ever see. The farthest back in time we can ever look. It is a fossil imprinted on the fabric of space itself, when the universe was a mere 380,000 years old, a cosmic toddler, in the grand scheme of things. To understand what this means, we have to journey back to that infant universe. It was not a spacious, dark void dotted with galaxies. It was a searing, blinding firestorm, an opaque, dense soup of energy and fundamental particles, a plasma so hot and thick that light could not travel freely. A photon would be born only to be immediately absorbed and scattered by a free electron, over and over again. The universe was a brilliant, impenetrable fog. But then a monumental transition occurred. As the universe expanded, it cooled. After about 380,000 years, it finally reached a temperature cool enough, around 3,000 degrees Celsius, for a miracle to happen. Electrons were captured by protons, forming the first stable atoms, mostly hydrogen. Suddenly the fog lifted. With no more free electrons to scatter them, photons, particles of light, were finally set free. They burst forth in every direction, and the universe became transparent for the very first time. That first flash of light, that moment of cosmic dawn, is what we detect today as the cosmic microwave background. But that light has not remained unchanged on its epic journey to us. The universe has stretched tremendously in the 13.8 billion years since that moment, and as space stretches, so does the light traveling through it. Its wavelengths have been stretched or redshifted, from visible light all the way down to the microwave part of the spectrum. Its energy has been sapped by the expansion of the universe, cooling it from thousands of degrees to just a few degrees above absolute zero, a frigid 270 degrees Celsius. So, what does this mean for us here and now? It means that this ancient light is everywhere. It fills every cubic centimeter of the space around you. It is passing through your body, through the walls of your home, through the earth itself right now. If you had an old-fashioned television set with snow on it, about 1% of that static was this echo of creation. The afterglow of the Big Bang is quite literally all around us. This is the oldest story ever told. It is not written on parchment or carved in stone. It is written in the cold microwave light that bathes the entire cosmos. It is a message in a bottle, sent to us from the very edge of time, and for a long time we didn't even know it was there. We were living inside the greatest archaeological dig site imaginable, unaware of the fossil buried in the very air we breathe. So the question we are left with is this: if this echo is real, what secrets does it hold? What can this faint, cold whisper from the dawn of time tell us about the origin of everything, about the nature of our universe and our own place within it? The answer, as we would discover, was more profound than anyone could have ever imagined. In the spring of 1964, at Bell Laboratories Field Station in Holmdel, New Jersey, a mystery began to unfold, one that would ultimately rewrite our understanding of the cosmos. Two young radio astronomers, Arno Penzias and Robert Wilson, found themselves facing a persistent and inexplicable problem. Their tool was the Holmdel horn antenna, a massive horn-shaped instrument originally built for satellite communication, but now being used for radio astronomy. Their goal was straightforward: to study faint radio waves from our galaxy. To do this properly, they needed to account for all background noise, calibrating their sensitive instrument to achieve a state of perfect quiet. Yet no matter what they did, their measurements were plagued by a constant low, steady hiss. a pervasive microwave static that was approximately 100 times more powerful than any expected background signal. This noise was unrelenting, present day and night, and seemed to emanate uniformly from every direction they pointed their giant horn. What began as a minor technical annoyance would soon become an obsession, leading them on a meticulous and at times comical quest for an explanation, unaware they were stumbling upon the most important cosmological discovery of the 20th century. Convinced the anomaly was a local issue, Penzias and Wilson embarked on a rigorous campaign of elimination. Their first suspect was the instrument itself. They meticulously disassembled and reassembled the electronics, checking every connection and component for flaws. The noise remained. They considered terrestrial interference from nearby New York City, but the signal's constancy, unchanging through day and night cycles and uniform across the sky, ruled out conventional sources like television signals, radar, or even the distant possibility of nuclear tests. Their attention then turned to the physical structure of the antenna. They discovered that a pair of pigeons had taken up residence in the giant horn, coating parts of the interior with what scientists diplomatically called a white dielectric material. Believing they had found the culprits, they evicted the pigeons, meticulously scrubbed the entire antenna, and sealed access points. Yet the stubborn hiss persisted. In a now legendary episode of scientific determination, the pigeons were eventually captured and shipped far away. But even this drastic measure failed to silence the pervasive static. After months of exhaustive effort, they had eliminated every conceivable source of error. The noise was real, measurable, and seemingly came from the universe itself. It was equivalent to a temperature of about 3.5 degrees above absolute zero, a faint but undeniable signal with no apparent origin. Just 40 miles away at Princeton University, a team of physicists led by Robert Dicke was working on a completely different problem. They had resurrected the Big Bang theory and predicted that if the universe had indeed begun in a hot, dense state, it should have left behind a cool, remnant glow, a cosmic background radiation that would permeate all space. Dicke and his team were actively building a radio receiver specifically designed to detect this primordial echo. They were theoretical pioneers searching for a ghost, while at Bell Labs, Penzias and Wilson were practical engineers trying to exercise one. The connection between these two endeavors was made through a mutual colleague, Bernard Burke, who, upon hearing of the Bell Labs team's pigeon problem, recognized its potential significance. He suggested that Penzias call the Princeton group. The resulting phone call and subsequent meeting would become a landmark moment in scientific history. As Penzias and Wilson described their inexplicable noise, their meticulous elimination process, and their evicted pigeons, the Princeton team immediately understood the profound implication. The persistent static wasn't an instrument flaw. It was the cosmic microwave background radiation, the cooled and redshifted afterglow of the Big Bang itself. The discovery was monumental. Penzias and Wilson had accidentally found the oldest light in the universe, a fossil from when the cosmos was just 380,000 years old. This radiation, now cooled to mere degrees above absolute zero by the universe's expansion, was the definitive evidence that confirmed the hot Big Bang theory over its rivals. It was a uniform whisper from the dawn of time, bathing the entire cosmos and passing through everything, including our own bodies at every moment. For their accidental discovery, which transformed cosmology from speculation into a precision science, Penzias and Wilson were awarded the 1978 Nobel Prize in Physics. Their story remains a powerful testament to the role of serendipity in science, demonstrating how careful observation, persistent troubleshooting, and an openness to unexpected results can lead to the most profound truths. They had set out to eliminate a nuisance and instead heard the faint cooling breath of creation, the echo of the universe's birth. The persistent hiss that bedeviled Penzias and Wilson was far more than just an anomalous reading. It was a message from the edge of time itself. When the significance of their discovery sank in, it revealed this signal to be the cosmic microwave background radiation, CMB, and in doing so it gave humanity its first and only baby picture of the entire universe. This is not a metaphor. The CMB is a genuine snapshot, a fossilized image of what the cosmos looked like at the tender age of 380,000 years. To understand this picture is to understand the moment our universe became recognizable. Before this moment, The universe was fundamentally alien. For the first several 100,000 years after the Big Bang, the cosmos was an opaque, searingly hot plasma, a dense and violent soup of protons, electrons, and light. Photons, particles of light, could not travel freely. They would zip a short distance only to be immediately scattered, absorbed, and re-emitted by a free electron. It was a brilliant, blinding fog, a roaring furnace where matter and radiation were locked in a constant chaotic dance. If you had been there, you would have seen nothing but a uniform, glowing brilliance in every direction, with no stars, no galaxies, no structure, only a raging, opaque inferno. The creation of the CMB marks the moment this fog lifted. As the universe relentlessly expanded, it cooled. By the time it reached its 380,000th year, the temperature had dropped to a cool 3,000 degrees Celsius. At this critical threshold, a fundamental transition occurred, an event cosmologists call recombination. The universe finally became cool enough for electrons to be captured by protons, forming the first stable neutral atoms, mostly hydrogen and helium. This was the moment of cosmic clarity. With the electrons now bound into atoms, the highways of the universe were suddenly cleared. The photons, which had been trapped in the plasma, were suddenly set free. They burst outward in every direction, and for the first time, light could travel across the cosmos without impediment. The universe became transparent. The flash of light from that moment of transparency is what we detect today as the CMB. Every point in space erupted with light, and that light has been traveling ever since. When we point our telescopes at the sky, we are capturing photons that have been on an uninterrupted journey for 13.8 billion years. They are the oldest things we can ever see. The moment of recombination acts as a cosmic wall. We cannot see beyond it with light because light before that time was not free to travel. The CMB is the ultimate barrier, the first page in the observable universe's history book. But this baby picture has aged. The universe has expanded by a factor of over 1,000 since the CMB was emitted. This cosmic stretching has a profound effect on light, performing a transformation known as redshift. The wavelengths of those primordial photons have been stretched along with the fabric of space itself. They have been pulled from the vibrant short wavelengths of visible light, the brilliant glow of a hot plasma, all the way down to the long, low-energy wavelengths of microwaves. Their energy has been sapped by the expansion, cooling them from 3,000 degrees to a mere 2.7 degrees above absolute zero. The brilliant, visible light flash of the early universe has been faded and cooled into the faint microwave whisper we detect today. This is why the CMB is a microwave background. It is the cooled and stretched relic of that first flash, and it is everywhere. It perfectly uniformly fills the entire universe, a bath of radiation that permeates every cubic centimeter of space. It is passing through the room you are in, through your body, through the earth at this very moment. It is the most perfect black body radiator ever measured in nature, a testament to its origin in a thermal, uniform state. However, this initial picture of perfect uniformity held a deeper secret. The first satellite designed to study the CMB in detail, COBE, confirmed its near-perfect blackbody spectrum but also made a discovery of equal importance. The CMB is not perfectly smooth. Imprinted upon this uniform background are tiny, minuscule fluctuations, anisotropies, variations in temperature, on the order of 1 part in 100,000. These tiny ripples are the most important part of the baby picture. They are the cosmic seeds of all structure. They represent regions of slightly higher and lower density in the early plasma, the gravitational blueprints for everything that would follow. From these infinitesimal wrinkles would grow, over billions of years, the vast cosmic web of galaxies, clusters, and superclusters. The CMB is therefore not just a baby picture. It is a predictive map. It shows us the initial conditions, the slight unevenness that gravity would amplify into the magnificent and structured cosmos we inhabit today. In its faint cold light, we see the origin of our entire cosmic home. The discovery of the cosmic microwave background did more than just add a new phenomenon to the astronomical catalog. It single-handedly ended one of the most profound scientific debates of the 20th century. For decades, cosmologists had been divided between two competing models of the universe, the steady-state theory and the Big Bang. The conflict was not merely technical. It was a battle over the fundamental nature of reality, whether the universe was eternal and unchanging, or whether it had a definite, dramatic beginning. The CMB, that faint hiss in a New Jersey antenna, would provide the conclusive evidence, becoming the smoking gun that firmly established our cosmic origin story. The steady-state theory, championed by figures like Fred Hoyle, Herman Bondi, and Thomas Gold, was an elegant and philosophically appealing concept. It proposed that the universe had no beginning and would have no end. It was infinite in both time and space. To account for the observed expansion of the universe where galaxies are moving apart, the theory suggested that new matter is continuously and slowly created in the voids left behind by the expansion. This would maintain a constant average density forever. In this model, the universe on a large scale always looks the same. It is perpetually renewing itself, with no moment of creation and no ultimate fate. It was a universe that simply was. The rival Big Bang theory, a name coined somewhat mockingly by Hoyle himself, presented a radically different vision. It proposed that the universe we observe exploded forth from a state of infinite density and temperature, a singularity, at a finite moment in the past. Since that initial event, the universe has been expanding and cooling. This model was dramatic and transformative, implying a definite beginning and a cosmic evolution. For much of the early 20th century, the evidence was circumstantial. Edwin Hubble's observations of receding galaxies confirmed the expansion, which was consistent with both theories. The steady-state theorists argued that expansion did not necessarily imply a beginning. It could simply be a perpetual state of affairs. The critical difference between the two theories, the point where their predictions irreconcilably diverged, concerned the past. The Big Bang model made a bold and testable prediction. If the universe was once in an ultra-hot, ultra-dense state, the remnants of that primordial fireball should still be observable today. As the universe expanded, the radiation from that initial state would have cooled, but it should still exist, filling all of space as a uniform, low-temperature background glow. This was a direct consequence of the physics of a hot, dense beginning. In the 1940s, physicists like George Gamow, Ralph Alpher, and Robert Herman had even calculated the expected temperature of this relic radiation, estimating it should have cooled to about 5 degrees above absolute zero. They predicted the existence of what we now call the CMB. The steady-state theory, by its very definition, could not allow for such a relic. In an eternal universe with no beginning, there was no primordial fireball. There was no moment of extreme heat and density whose afterglow could persist. The universe was, on average, the same at all times. Therefore, there should be no all-pervading background radiation from a hot, dense past. The existence of such a signal would be fatal to the theory. This was the state of play in 1964 when Arno Penzias and Wilson, completely unaware of the cosmological implications, began their fight against the persistent noise in their horn antenna. They had no stake in the theoretical battle. They were simply trying to do clean radio astronomy, but by meticulously eliminating every possible local source of that noise, from pigeon droppings to electronic faults, they were left with an inescapable conclusion. The signal was real. It was cosmic and it was uniform. When news of this discovery reached the Princeton team led by Robert Dicke, who were actively building a detector to find the very relic Gamow and others had predicted, the significance was immediately clear. Dicke famously turned to his colleagues and said, "Well, boys, we've been scooped. The Bell Labs signal matched the predicted characteristics of the cosmic background radiation perfectly. It was isotropic, it was in the microwave band, and its temperature, measured at 3.5 Kelvin, was remarkably close to the theoretical predictions. The discovery was the smoking gun." The steady-state theory had no mechanism to explain this pervasive, cool background radiation. It was an artifact from a specific hot epoch in the universe's history, an epoch that the steady-state model explicitly denied. The CMB was the cooled ashes of the primordial fire, the definitive evidence that the universe was not eternal and unchanging, but had a definite, hot, and dense beginning. It transformed the Big Bang from a compelling but unproven hypothesis into the cornerstone of modern cosmology. In that faint universal hiss, scientists heard the echo of the first moment of time, finally settling the great debate and giving us our modern story of cosmic birth. To truly understand the nature of the cosmic microwave background, we must embark on a journey back in time, to the specific moment it was born. This is not a journey to the Big Bang itself, but to a pivotal event that occurred 380,000 years later, a cosmic transition of such profound importance that it made the observable universe possible. This event is known as the era of recombination, and it marks the moment the universe transformed from an opaque, blazing fog into a transparent, dark expanse. Let us visualize the universe before this moment. For the first several 100,000 years of its existence, the cosmos was a searingly hot and dense plasma. The temperature was so immense, billions of degrees, that atoms could not hold together. Protons and electrons, the building blocks of matter, existed in a free state, buzzing about in a chaotic, energetic soup. Crucially, light was trapped. Photons, the particles of light, could not travel any meaningful distance. A photon would be emitted only to be almost instantly scattered or absorbed by a free electron. The universe was a brilliant, impenetrable glare, a thick, swirling fog of energy and charged particles. If you could have been there, your entire field of vision would have been a uniform, blinding white, no stars, no blackness, just a featureless, glowing prison of light. The key to the transformation was the relentless expansion of the universe. As space stretched, it cooled. Think of it like a vast cosmic gas expanding and losing its heat. After about 380,000 years, the universe had cooled to a temperature of around 3,000 degrees Celsius, about 5,400 degrees Fahrenheit. While this is still incredibly hot by human standards, it was a critical threshold for the fundamental forces of nature. At this temperature, the frantic dance of particles finally slowed enough for something miraculous to happen. Electrons could be captured and held in orbit around atomic nuclei, primarily protons, to form the first stable, neutral atoms, hydrogen and helium. This process is called recombination, a slight misnomer as the particles were combining for the first time, not recombining. But the name has stuck. As this epoch unfolded, the universe underwent a dramatic change in its very nature. The free electrons, which had been such effective blockers of light, were now being locked away inside atoms. The fog was lifting. The universe, for the first time, was becoming a place where light could travel freely. This is the moment the cosmic microwave background was born. The photons that had been trapped in the plasma for 380,000 years were suddenly set free. As the last electrons were captured into atoms, the universe became transparent. In an instantaneous cosmic flash, every part of space released its pent-up light. These photons, once trapped in a local dance with matter, began their epic journeys across the expanding cosmos. The surface of last scattering, as this moment is called, is not a surface in space like the skin of a balloon. It is a moment in time, a horizon in every direction we look. When we point our telescopes at the CMB, we are seeing the light from that moment of transparency, from that final flash as the cosmic fog lifted. But what we see today is not the brilliant, hot light that was initially released. The universe has been expanding for the 13.8 billion years since that flash. This expansion has stretched the very fabric of space-time, and with it, the wavelengths of that primordial light. The photons have been cosmologically redshifted. Their energy has been dramatically sapped by the expansion. The vibrant, visible light that filled the young universe, aglow with the intensity of the surface of a star, has been stretched and cooled into the faint microwave radiation we detect today. The brilliant, visible light flash of the early universe has been faded into the cold, microwave whisper of the CMB, now just 2.7 degrees above absolute zero. Therefore, the CMB is not just a picture. It is a literal snapshot of the universe at the age of 380,000 years. The tiny temperature fluctuations we map, the slightly warmer spots and cooler spots, are the imprints of the slight density variations in that primordial plasma. They are the seeds of all future structure. The slightly denser regions, revealed as slightly cooler spots in the CMB, a complex effect of gravitational redshift, would over billions of years be amplified by gravity to collapse into the first stars, galaxies, and the vast cosmic web. So when we study the cosmic microwave background, we are performing the ultimate act of archaeology. We are looking back to the moment the universe became transparent, to the time when it was a simple hot plasma of hydrogen and helium, just beginning to imprint the gravitational patterns that would one day become everything we know. The CMB is the final glow of the cosmic fireball, the last echo of a time when the universe was a brilliant fog, and the first light of a transparent cosmos that would eventually give rise to us. The discovery of the cosmic microwave background was a monumental victory for cosmology, but it presented scientists with a new and profound puzzle. The initial measurements from Penzias and Wilson, and subsequent balloon and ground-based experiments, pointed to a radiation field that was astonishingly, almost unnervingly, uniform. No matter which direction they looked, the temperature of this ancient light was the same, to within a tiny, almost imperceptible fraction of a degree. This perfect smooth glow was a problem. A universe that began in a hot, dense state and expanded should indeed have a uniform background, but it shouldn't be this perfect. This perfection was, in fact, a profound cosmological crisis. Why was this a problem? Imagine the universe at 380,000 years old, as revealed by the CMB. If it were perfectly smooth, with matter and energy distributed with exact uniformity, then gravity would have had nothing to work with. There would have been no slight overdensities, no gravitational seeds for it to amplify. In a perfectly smooth universe, gravity pulls equally in all directions, resulting in a cosmic stalemate. The gas would have remained a diffuse, featureless haze forever. There would be no clusters of galaxies, no galaxies themselves, no stars, no planets, and no us. The existence of the complex cosmic structures we see today was living proof that the early universe could not have been perfectly smooth. There had to be imperfections, tiny initial lumps that gravity could nurture over billions of years into the grand architecture of the cosmic web. Yet the CMB, our only snapshot of that early time, showed a near-perfect smoothness. Where were the seeds? This was the state of uncertainty that the Cosmic Background Explorer, COBE satellite was launched to resolve in 1989. Its mission was to measure the CMB with a precision far beyond what was possible from Earth's surface, to map its temperature across the entire sky, and finally determine if the theorized imperfections were real. For the first year, the data only deepened the mystery. COBE confirmed the CMB's stunning uniformity with breathtaking precision, measuring it as a perfect blackbody radiator. The glow was, for all intents and purposes, perfect. It seemed the universe had handed cosmologists a paradox, a smooth beginning that somehow led to a lumpy present. Then, on April 23, 1992, the COBE team, led by George Smoot and John Mather, made an announcement that sent shockwaves through the scientific community and made front-page news around the world. After years of painstaking data analysis, they had found them. Imprinted on the perfect 2.7-degree background were tiny, fluctuating anisotropies, minuscule variations in temperature from one patch of the sky to another. These fluctuations were incredibly faint, a mere 30 to 50 millionths of a degree Celsius. To grasp this scale, it is the equivalent of looking at a smooth, black and white photograph and discovering variations in the shade of gray, so subtle that they are only 1 part in 100,000. The human eye could never perceive them, but to a cosmologist they were the most important features imaginable. The COBE map of the sky, often described as a child's first scribble, was in reality the most detailed baby picture of the universe ever taken. Those tiny splotches of red and blue superimposed on a field of green were not flaws. They were the blueprints for all of creation. The slightly warmer, denser, and cooler, less dense spots were the fossilized imprint of the primordial density fluctuations. They represented regions where the gravitational pull was ever so slightly stronger or weaker. Over the next 13.8 billion years, gravity would act like a cosmic amplifier. The slightly denser regions, revealed as slightly cooler spots due to a complex gravitational effect, would pull in more and more matter from their surroundings. They would grow, collapse, and eventually form the first stars and galaxies. The great cosmic voids we see today are the descendants of the slightly warmer, underdense regions in the COBE map. The discovery of these anisotropies was the final, crucial piece of evidence that cemented our modern understanding of cosmic evolution. It solved the structure problem, elegantly bridging the gap between the smooth early universe and the lumpy one we inhabit. It confirmed that the seeds of all complexity, from the smallest galaxy to the largest supercluster, were sown in the first fleeting moments of the Big Bang, written in the faint temperature variations of the CMB. The glow was not perfect, and in its beautiful, subtle imperfections lay the entire history and future of the cosmos. COBE had not just mapped the sky, it had found the genetic code of the universe, a recipe etched in light for building everything we see. The COBE satellite's revelation was a landmark achievement, but it was like a cartographer discovering a new continent from 1,000 miles offshore. The map was real, but its features were blurry, its details lost in the fog of distance. The tiny temperature fluctuations in the cosmic microwave background were confirmed, but their true nature, their specific size, distribution, and pattern remained to be decoded. This was not merely an academic exercise. It was an act of reading the ultimate blueprint, for encoded in these anisotropies was the complete set of instructions for building the universe as we know it. These faint ripples were the gravitational seeds from which every galaxy, star, and planet would eventually grow. To understand how this works, we must first grasp what these temperature variations represent. The CMB is a snapshot of the universe at the moment of recombination, when the opaque plasma fog cleared. At that time, the universe was not perfectly smooth. It was filled with sound waves propagating through the hot, dense soup of particles and radiation. Think of the early universe as a vast, seething cauldron, with regions rhythmically compressing and expanding. Where the plasma was compressed, it was slightly hotter and denser. Where it was rarefied, it was slightly cooler and less dense. These are the fluctuations we see in the CMB temperature map. But hot and cold here are relative terms. We are talking about differences of mere millionths of a degree, yet in cosmology it is the gradient that matters. A slightly denser region has a slightly stronger gravitational pull. This is the crucial link between the smooth early universe and the structured one we see today. After recombination, matter, now neutral and decoupled from light, was free to feel the full, unmediated pull of gravity. Those regions of the CMB that were a few microdegrees warmer, which correspond to areas of higher density due to gravitational redshift, began to act as gravitational anchors. Over the next several 100 million years, they slowly pulled in more and more dark matter and gas from their surroundings. What began as a microscopic density contrast was amplified into a macroscopic one. A ripple became a hill, the hill became a mountain, and the mountain eventually collapsed under its own gravity to form the first protogalactic clouds and, ultimately, the glittering cities of stars we call galaxies. But the blueprint held more specific information than just the location of future structures. The most powerful insights came from analyzing the statistical properties of these fluctuations, not just their existence, but their pattern. When scientists created a graph plotting the angular size of the fluctuations against their relative strength, a profound pattern emerged. This power spectrum revealed a series of distinct peaks, and these peaks were the Rosetta Stone for decoding the cosmos. The first and highest peak was the most fundamental confirmation. It revealed the characteristic size of the fluctuations at the time of recombination, a scale set by the distance a sound wave could travel in the universe's first 380,000 years. This sonic horizon is a fundamental ruler etched into the sky, and its measured size confirmed the geometry of the universe is flat, a critical finding that dictates the universe's ultimate fate and the amount of matter and energy it contains. The second peak was even more revealing. It is sensitive to the density of ordinary matter, the protons and neutrons that make up stars, planets, and us. The height of this peak told us that ordinary baryonic matter makes up only about 5% of the total content of the universe. The rest, it implied, must be something that does not interact with light and thus could not participate in the sound waves in the same way. This was a powerful, independent confirmation of the existence of dark matter. The third and subsequent peaks provided further constraints, fine-tuning our understanding of the total density of the universe and the balance between dark matter and dark energy. In essence, the precise harmonic structure of these peaks, the cosmic music of the infant universe, allowed scientists to read off the fundamental parameters of our reality with stunning precision. The composition, geometry, and fate of the entire cosmos were written into the statistical whisper of those temperature variations. Therefore, the anisotropies in the CMB are far more than just the seeds of structure. They are a frozen record of the physical conditions of the infant universe. Every galaxy cluster, every spiral arm, every solitary star drifting in the void is the direct descendant of a specific, infinitesimal fluctuation on that ancient map. The immense filamentary structure of the cosmic web, with its great clusters at the intersections and vast voids in between, is simply the grown-up version of the speckled pattern we see in the CMB. In those faint, cold ripples, we see the complete and utter contingency of our own existence. our Milky Way galaxy, our Sun, our Earth, all exist because of the particular gravitational well into which our corner of the universe fell 13.8 billion years ago. The blueprint of reality is not a metaphor. It is a precise mathematical map, and we are living proof of its astonishing accuracy. The COBE satellite had given us the first grainy photograph of the infant universe, confirming the existence of the primordial wrinkles that seeded all structure. But its vision was blurry, like looking through a frosted window. The picture was revolutionary, but the details, the precise size, shape, and nature of those fluctuations remained tantalizingly out of focus. To move from a confirmation of the theory to a precise measurement of the universe's fundamental parameters, we needed a sharper lens. This quest for clarity was the driving force behind two legendary missions: the Wilkinson Microwave Anisotropy Probe, WMAP, and the Planck satellite, which together would transform cosmology from a field of grand ideas into one of exquisitely precise numbers. Launched in 2001, MAP was the next great cartographer of the cosmos. Its design was a masterpiece of orbital engineering. Instead of orbiting the Earth, where our planet's heat and microwave emissions would interfere, it was sent to the L2 Lagrange point, a stable gravitational point in space about 1 million miles from Earth, always on the opposite side from the Sun. Here, in the profound quiet and cold of deep space, WMAP could listen to the cosmic whisper without interruption. For 9 years it scanned the entire sky, its twin telescopes gathering data with a sensitivity and angular resolution far beyond COBE's capabilities. The result, released in a series of landmark datasets, was nothing short of breathtaking. The WMAP team produced a full sky map of the CMB that was orders of magnitude more detailed than COBE's. The child's scribble was now a detailed anatomical chart. The tiny temperature variations were now clearly resolved, revealing a complex tapestry of hot and cold spots. But the true power of WMAP lay not just in the beautiful image but in the data behind it. By performing a sophisticated statistical analysis on the map, creating what is known as a power spectrum, scientists could extract the universe's vital statistics with unprecedented precision. The MAP data allowed cosmologists to measure the age of the universe with stunning accuracy, 13.77 billion years, with an uncertainty of less than 1%. It pinned down the composition of the universe: 4.6% ordinary atoms, 24% dark matter, and 71.4% dark energy. It confirmed with overwhelming evidence that the geometry of the universe is flat, and it provided a detailed timeline of key cosmic events, such as the formation of the first stars, which it determined began shining about 400 million years after the Big Bang. WMAP had turned the CMB from a picture into a precision tool, but the pursuit of perfection did not stop there. If WMAP provided a high-definition map, the European Space Agency's Planck satellite, launched in 2009, was designed to deliver an ultra-high-definition IMAX quality version. Planck was even more sensitive than WMAP and observed at a wider range of frequencies, allowing it to meticulously subtract foreground contamination from our own Milky Way galaxy with surgical precision. Its instruments were so cold and sensitive they could detect temperature variations of a few 10 millionths of a degree. The Planck map, released in 2013 and refined with its final data in 2018, is the most detailed baby picture of the universe we will likely have for generations. It is the pinnacle of CMB observation. The level of detail is so fine it is almost incomprehensible. The map contains over 50 million pixels of information about the early universe. Planck's measurements sharpened the numbers from WMAP, providing the most precise values we have for the cosmological parameters. It refined the age of the universe to 13.8 billion years, and the composition to 4.9% ordinary matter, 26.6% dark matter, and 68.5% dark energy. More than just refining numbers, Planck's exquisite data allowed scientists to test the most fundamental theories of the universe's birth, such as inflation, with unprecedented rigor. It put stringent constraints on different inflationary models and confirmed the basic paradigm to a remarkable degree. It also revealed some subtle, puzzling anomalies. For instance, a puzzling asymmetry in the average temperature between one half of the sky and the other, and a confirmed cold spot that is larger than the standard model can easily explain. These are not errors, but potential clues, tiny cracks in our understanding that may point toward new, deeper physics. Together, Map and Planck completed a journey that began with a frustrating hiss in a New Jersey antenna. They transformed the CMB from a conceptual cornerstone into a rich, quantitative database. They gave us a standard model of cosmology so precise that we can now speak of the universe's composition, age, and geometry with more confidence than we once had about the structure of the atom. These missions did not just map the infant cosmos, they provided the definitive weights and measures for reality itself, establishing a foundation for all of cosmology upon which every new discovery must now be built. They gave us a birth certificate for the universe, written in the cold ancient light of its first dawn. The maps produced by Map and Planck are far more than just beautiful pictures. They are complex cryptographic messages left over from the dawn of time. By learning to decode the subtle patterns in the cosmic microwave background, scientists have been able to perform the ultimate act of cosmic accounting, deriving a precise recipe for the entire universe. The result is both humbling and astonishing. The stuff we have always considered the universe, the atoms that make up stars, planets, and us, constitutes a mere 5% of the total. The remaining 95% is composed of two mysterious, invisible components, dark matter and dark energy, whose natures remain one of physics' greatest mysteries. The CMB is the ledger that revealed this shocking cosmic budget. The key to this decoding lies in the detailed statistics of the CMB's temperature fluctuations, known as its power spectrum. Think of the early universe as a pond into which a handful of pebbles has been tossed. The ripples from each pebble spread out and interfere with one another, creating a complex pattern of waves. By analyzing this pattern, the specific sizes and heights of the waves, you can deduce the properties of the pond itself, such as its depth and the consistency of its water. The CMB is the frozen record of the ripples in the primordial plasma, and its power spectrum allows us to deduce the fundamental ingredients of the cosmos. The first and most prominent wave or peak in the spectrum tells us about the overall geometry and total density of the universe. Its measured size confirmed that we live in a universe with a flat geometry. For the universe to be flat, its total density must be at a very specific critical value. This single measurement told us that the combined total of all matter and energy, ordinary matter, dark matter, and dark energy, must add up to this critical density. It gave us the grand total of the cosmic ledger. It is the second and third peaks, however, that allow us to break down that total into its constituent parts. Here is where the CMB acts as a brilliant forensic tool for separating dark matter from ordinary matter. In the first 380,000 years, the universe was a tight coupling of ordinary matter, protons, electrons, or baryons, and light, photons. The pressure from the photons pushed against the gravity of the matter, creating oscillating sound waves in the hot plasma. Ordinary matter interacts with light, dark matter does not. This difference is crucial. The photons exerted radiation pressure on the ordinary matter, helping to push it back out after a gravitational collapse, which enhanced the oscillations. Dark matter, being immune to this light pressure, simply clumped together under gravity without being pushed back. The relative heights of the second and third peaks in the power spectrum are exquisitely sensitive to this difference. A universe with more ordinary matter would have a more pronounced bounce from radiation pressure, suppressing the height of the third peak relative to the second. The precise pattern measured by Map and Planck reveals a universe where ordinary matter makes up only about 5% of the critical density. The majority of the matter, about 27% of the universe, must be this invisible, non-interacting substance we call dark matter. This leaves a staggering 68% of the universe unaccounted for by matter of any kind. This is where dark energy enters the recipe. While the peaks in the CMB spectrum are primarily set by the conditions in the early universe, they also hold a subtle imprint of what happened much later. The very first peak, which sets the apparent angular size of the fundamental ripples, is a standard ruler. We know its physical size from theory. By measuring how big it appears on the sky, we can triangulate the distance to the CMB and thus the geometry of the universe across 13.8 billion years of expansion. The results from this geometric measurement were definitive. The universe has not only expanded, but the expansion has accelerated over the latter half of its life. To cause this acceleration, there must be a dominant, component in the cosmic ledger that exerts a repulsive gravitational force. This component is dark energy, and it makes up the remaining 68% of the universe. It is the price we pay for a flat universe after accounting for the small amounts of ordinary and dark matter. Therefore, the faint pattern of hot and cold spots in the CMB is a cosmic barcode that, when scanned, reveals the complete inventory of the cosmos. It tells us that we are living in a universe dominated by mysteries. 68% is dark energy, a repulsive force driving the cosmos apart. 27% is dark matter, an invisible scaffolding that holds galaxies together. And a mere 5% is the ordinary atomic matter that forms every star, planet, and living thing we have ever seen or touched. The CMB is the ultimate reality check, a profound reminder that our perception of the universe based on the light we see is but a flickering candle in a vast, dark, and enigmatic cathedral. One of the most profound revelations from the cosmic microwave background is an answer to a question that has haunted philosophers and scientists for millennia. What is the shape of the universe? Is it curved in on itself like a sphere? Does it bend away like a saddle? Or is it, against all odds, fundamentally flat? The patterns in the CMB provide a definitive answer, and it has staggering implications for the universe's origin, its fate, and the very nature of reality. The universe, on its largest observable scales, is geometrically flat. To understand what cosmologists mean by flat, we must move beyond our everyday intuition. We are not talking about a two-dimensional sheet of paper, but the large-scale geometry of the three spatial dimensions of the cosmos. A useful, though simplified, analogy is to imagine the universe in two dimensions. In this analogy, a flat universe would be like an infinite, uncurved plane. A closed universe would be the surface of a sphere, finite but without an edge. An open universe would be the surface of a saddle, curving away from itself in all directions. Each of these geometries has a dramatic consequence for the fate of the universe and the behavior of light. In a closed spherical universe, parallel beams of light would eventually converge. In an open, saddle-shaped universe, they would diverge. But in a flat universe, parallel beams of light remain parallel as they travel across the cosmos. This property of light is the key to how the CMB measures the universe's shape. The CMB provides us with a built-in cosmic ruler. The ripples imprinted on it, the hot and cold spots, have a known physical size. This size is determined by the distance a sound wave could travel in the plasma of the early universe before recombination, a distance known as the sound horizon. It is a fixed standard ruler, etched into the sky when the universe was only 380,000 years old. When we look at the CMB map, we are seeing this ruler projected onto the celestial sphere. How large this ruler appears to us depends entirely on the geometry of the space-time between us and the CMB. Think of it like looking at a tile floor. If the floor is flat, the tiles will appear a certain size. But if the floor is curved like a sphere, the tiles in the distance will appear larger or smaller, depending on the curvature. The most prominent feature in the CMB power spectrum, the first and highest peak, corresponds to the angular size of this fundamental sound horizon ruler. For nearly 2 decades, experiments like Boomerang and Maxima, and then definitively by W. Map and Planck, have measured this angular size with exquisite precision. The result is clear. The ruler appears to be almost exactly the size predicted for a perfectly flat universe. The beams of light from the edges of these primordial ripples have traveled 13.8 billion years to reach us, and they have remained essentially parallel. This finding of flatness is not just a geometric curiosity. It is a profound clue about the universe's contents and its origin. In the theory of general relativity, the geometry of the universe is determined by its total density of mass and energy. There is a specific critical density required to make the universe flat. A density higher than this would cause it to curve into a sphere. A lower density would cause it to curve into a saddle. The CMB's flatness tells us that the average density of our universe is, with remarkable precision, exactly at this critical value. This single measurement, therefore, acts as a cosmic scale. It told us that the combined mass energy of everything in the universe, ordinary matter, dark matter, radiation, and dark energy, must add up to the critical density. This was the first step in creating the precise cosmic recipe of 5% ordinary matter, 27% dark matter, and 68% dark energy. The flatness demanded it. Furthermore, this perfect flatness is deeply connected to the theory of cosmic inflation, a universe that begins with any arbitrary curvature and then undergoes an exponential, faster-than-light expansion in its first moments would be stretched to an apparent flatness, just as inflating a balloon to an immense size makes the surface of any small patch appear flat. The CMB's measurement of flatness is one of the strongest pieces of evidence we have that such an inflationary epoch occurred. The implications are staggering. A flat universe is likely to be infinite in extent. Its ultimate fate is not a big crunch, as in a closed universe, or a big rip, as in some open models, but a perpetual accelerating expansion driven by dark energy, leading to a cold, dark, and dilute end known as the heat death. The geometry also constrains theories of extra dimensions. For the universe to appear flat in 3 dimensions, any extra spatial dimensions proposed by string theory must be compactified, or curled up on a scale too small for us to perceive. In the end, the CMB tells us that the fabric of our cosmos, on the grandest of scales, is simple, Euclidean, and flat. It is a geometry we learned in high school, but one that, on a cosmic scale, reveals a universe finely tuned to a specific density, born from a violent inflationary burst and destined to expand forever into infinite silence. The discovery of the CMB's temperature anisotropies was a triumph. The subsequent detection of its polarization was a refinement. But within that polarization lies a specific, elusive pattern that represents the single greatest prize in modern observational cosmology: the signature of primordial gravitational waves. This signal, known as B-mode polarization, is not just another data point. It is a direct window into the universe's very first instant, a potential glimpse of the inflationary epoch itself, and the hunt for it is pushing the limits of our technology and our understanding of physics. To understand B-modes, we must first understand how the CMB becomes polarized. When the CMB photons were finally set free during recombination, they did not just carry a record of temperature. They also carried a record of their last interaction with matter. Just before recombination, the primordial plasma was a seething sea of electrons being buffeted by the sound waves and radiation that filled the universe. When a photon scatters off an electron, the interaction can polarize the light, meaning its electric field vibrates in a preferred direction. The pattern of this polarization across the sky is a fossilized imprint of the velocity of the electrons in that final instant. It tells us not just how dense the plasma was, but how it was moving. This polarization comes in 2 fundamental types, which physicists describe by their mathematical curl properties. Borrowing from the language of electromagnetism, E-mode polarization is a curl-free or gradient pattern. It looks like radial patterns or centipedes on the sky, and it is generated by the relatively straightforward motions of matter, the incoming and outgoing flows of the primordial sound waves. E-modes were first definitively detected in 2002 and have since become a standard part of the CMB toolkit, providing a powerful cross-check on the story told by the temperature anisotropies. B-mode polarization is different. It is a curl pattern, one that has a distinct swirly character, like the pattern of water swirling down a drain. This kind of pattern cannot be created by the simple, scalar clumping of matter that produces the sound waves and the E-modes. To create a swirly pattern in the fabric of spacetime, you need a tensor force, a force that can stretch and squeeze space in perpendicular directions. And that is the exclusive domain of gravitational waves. The hunt, therefore, is for the B-mode polarization in the CMB that was imprinted by primordial gravitational waves. These are not the gravitational waves from merging black holes detected by LIGO and Virgo. Those are recent astrophysical events. Primordial gravitational waves would be a relic from the inflationary epoch itself. According to the theory, the violent exponential stretching of spacetime during inflation would have generated a background of these waves, ripples in the very fabric of reality that have been propagating through the universe ever since. As they passed through the plasma just before recombination, these ripples would have gently tugged and twisted the electrons, imparting a unique, swirly B-mode pattern onto the scattered CMB photons. Detecting this signal would be one of the most significant discoveries in the history of science. It would provide the first direct, physical evidence for the existence of the inflationary field, and offer a direct probe of physics at energies 1 trillion times higher than those achievable in the Large Hadron Collider. It would allow us to measure the energy scale of inflation itself, telling us just how violent the bang in the Big Bang truly was. In essence, it would be our first ever observational data from the inflationary epoch. The challenge, however, is that the signal is incredibly faint. The B-mode signal from primordial gravitational waves is predicted to be more than 1,000,000 times fainter than the temperature anisotropies we see so clearly. It is a whisper buried beneath a cacophony of other signals. Foregrounds are a massive problem. Our own Milky Way galaxy emits polarized light from interstellar dust and synchrotron radiation, both of which can mimic the B-mode signal. The gravitational lensing of the CMB by the large-scale structure of the later universe also converts some of the E-modes into a secondary, lensing B-mode signal, which creates a confusing background. The hunt has been dramatic. In 2014, the BICEP2 collaboration made a stunning announcement that they had detected the primordial B-mode signal. The excitement was short-lived, as a joint analysis with the Planck satellite later confirmed that the signal they saw was almost entirely due to polarized dust from our own galaxy. This episode highlights the extreme difficulty of the quest. Today, the hunt continues with ever more sensitive telescopes located at the driest, coldest places on Earth, the South Pole and the high Atacama Desert in Chile, where the atmosphere is too thin to block the faint microwave signal. These experiments, like the Simons Observatory and the upcoming CMB-S4 project, are deploying arrays of tens of thousands of superconducting detectors to map the CMB's polarization with unprecedented sensitivity, and to meticulously separate the galactic foregrounds from the true cosmological signal. The search for B-mode polarization is the cutting edge of cosmology. It is a high-stakes endeavor to find a ghostly signature from the dawn of time, a swirl in the ancient light that would confirm our grandest theory of origins and open a new window onto the quantum gravity era. It is a testament to our relentless drive to understand not just how the universe is, but how it came to be. The cosmic microwave background is our ultimate time machine. It carries us back 13.8 billion years to a universe that was a mere 380,000 years old. But as we gaze upon this detailed baby picture, we must confront a sobering and fundamental truth. This is the limit. The CMB is not just a snapshot. It is a wall, a brilliant opaque wall of light that marks the boundary of the observable universe and the absolute limit of what we can see with photons. Beyond it lies an epoch known as the Dark Ages, a profound and mysterious era that is, for now, hidden from our view. The reason for this wall is the very nature of the early universe. Before the moment of recombination that created the CMB, the universe was a plasma, a hot, dense soup of free protons, electrons, and photons. In this state, the universe was opaque. A photon could not travel more than a tiny fraction of an inch before being violently scattered, absorbed, and re-emitted by a free electron. Light was trapped, bouncing around in a brilliant, impenetrable fog. The universe was a glowing, uniform prison of energy. The CMB is the light from the moment that prison door swung open. When the universe cooled enough for electrons to be captured into atoms, the fog lifted instantaneously. The photons that had been trapped were suddenly set free, and they have been traveling in straight lines ever since, carrying a pristine image of that moment of liberation. When we detect a CMB photon, we are tracing its path directly back to its last scattering event 13.8 billion years ago. We cannot see any further because light from before that moment could not travel freely to us. The plasma acts as a perfect curtain, shielding the universe's very first acts from our view. So what lies in the darkness behind this brilliant curtain? The epoch between the Big Bang and the creation of the CMB is known as the Dark Ages. This is not a period of inactivity, but one of profound transformation, hidden behind the opaque plasma. In the first few minutes during a period called Big Bang nucleosynthesis, the universe was a nuclear fusion reactor, fusing protons and neutrons into the first light elements, hydrogen, helium, and trace amounts of lithium. This process set the elemental composition for the entire future universe. But it happened entirely within the blinding fog, after nucleosynthesis ended, and for the next several 100,000 years. The universe entered a relatively quiet yet crucial phase. It was still an opaque plasma, but it was expanding and cooling. The dominant physical process was the relentless competition between gravity and radiation pressure, setting up the sound waves that would later be frozen into the CMB. It was during this time that the slight quantum fluctuations from the inflationary epoch were amplified into the density, variations that would become the seeds of galaxies. The blueprint was being drawn, but the construction site was shrouded in a blinding light. The moment the CMB was released marked the true beginning of the cosmic dark ages in the traditional sense. With the universe now transparent and neutral, a profound darkness fell. There were no stars, no galaxies, no quasars. The only light was the fading afterglow of the CMB itself, redshifting into longer and longer wavelengths. The universe was a vast expanding sea of dark hydrogen and helium gas, punctuated only by the invisible, gravitational seeds of dark matter. It was a simple, quiet, and profoundly dark place. This cosmic night lasted for perhaps 100 to 200 million years. Then, within the densest knots of dark matter, the first pockets of gas began to collapse, heat up, and ignite. The first stars, known as population 3 stars, were born. These behemoths, thought to be hundreds of times more massive than our sun, lit up the darkness, ending the dark ages and beginning the cosmic dawn. Their intense ultraviolet radiation began to reionize the neutral hydrogen gas around them, tearing atoms apart and returning the universe to a plasma state, though this time, a much more diffuse and transparent one. This epoch of ionization is the next frontier. While we cannot see the first stars directly, we can see their effect on the CMB. As the CMB photons traveled through this newly reionized plasma, a small fraction of them were rescattered by the newly freed electrons. This imparted a distinct large-scale polarization pattern on the CMB, the E-mode polarization we can detect today. It is a faint secondary signature of the end of the Dark Ages, a ghostly echo of the first starlight. The CMB, therefore, is both a terminus and a starting point. It is the final curtain before the unseeable first act of the universe, a brilliant wall of last scattering. Yet encoded within its light is the story of what came immediately after its own release. To peer into the darkness before the CMB, we must rely on other messengers, like neutrinos or primordial gravitational waves, which could potentially carry information from the first instance, having traveled through the plasma unimpeded. For now, the universe's earliest childhood remains a hidden, formative period, a realm of fiery transformation whose secrets are locked behind the very light that gives us our most profound view of the cosmos.